chapter, we're going to see what happens when the regions we look at are circular. So in this section, we're looking at kind of circular two-dimensional shapes, and then next week we'll be looking at the equivalent in 3 dimensions, which won't be a sphere for us, it'll just be a cylinder. Okay, so it's convenient on occasions to work with coordinates different from Cartesian coordinates, which are like what you could call rectangular coordinates. When dealing with circular regions, it is in general more convenient to use polar coordinates rather than Cartesian. And what you get is, say if you're integrating over a circle, to turn your function of x and y into a function of r and theta. And I will explain what r and theta are. And one thing you might note is that dA is not dr by d theta, it's r by dr by d theta, and we will show this. So what are we going to show here? Yeah, so let's look at something. So if you look at a disk, there's a few things. So I'm going to draw a disk. That's supposed to be a circle. Now we're interested actually in the disk, the whole disk, not just the circle. Okay, so let's show that every single point satisfies the x coordinate squared plus the y coordinate squared is less than a. Now here a is the radius of the disk. So that'd be a, that'd be minus a, and look, whatever way you cut it, this will be the same. Now it's obviously not drawn symmetrically, but just imagine that I did actually manage to draw it symmetrically. So take a point, say here, let's call this the point xy, and we can say that the distance from xy to the origin is less than a. Now actually, if I include that xy could possibly be on the circle, it'll be less than or equal to a. Okay, now you've got the distance between 2 points formula, which by the way can be shown from Pythagoras theorem, but it's like, what is it? It's the square root x1 minus x2, which here would be x minus 0 squared, plus y minus 0 squared less than or equal to a, and square both sides. And note that x minus 0 all squared is just x squared. So if I square both sides, it'll get rid of the square root. Get x squared plus y squared less than or equal to a squared. So all of the coordinates of the form x squared plus y squared less than or equal to a squared is the disk of radius a, and it includes the circle but also all the interior points. So there's an alternative set of coordinates to x and y, which is r and theta. Now basically it's like magnitude and direction. So r is like the magnitude and theta is like the direction. So if you take a point here, the magnitude is the length of this, that's the r, and the theta is the angle that it makes with the positive x-axis. So you can give you can describe a point using r and theta instead of x and y. It's like magnitude and direction. And if you do a little bit of trigonometry or what have you, so let's call this bit, we'll just call it adjacent, and this bit we'll call opposite, because we're going to be thinking about trigonometry. So let's say the sine of theta, I've written this kind of in the wrong place. Well, I'll go up to the top. So the cos of theta is equal to adjacent over hypotenuse, and in this forms a little right angle triangle. So the adjacent I'm calling a, and the hypotenuse is r. So I get that the a there is, the adjacent is r cos theta by multiplying both sides by r, and similarly I have that the opposite is r sine theta. And you might notice that the opposite, the length of the adjacent is exactly the x coordinate. So the x coordinate is r cos theta, and the y coordinate is the same as the length of the opposite, which is r sine theta. So we have that if we have an x and you're converting to what are called, these are going to be polar coordinates. The polar somehow meaning round, or cos theta, and y is our sine theta. Now the other thing we have to do is look at a little bit of a. So what we can do to find this is we can do big pizza slice minus little pizza slice. So rather than doing a dA like this, show you the type of dA we do. Pizza, so I call it a little bit of pineapple. It's a pineapple slice. Okay, now what you can do here is that so we're going to call this dA, and it'll be the big pizza slice minus the little pizza slice. Now we need to pick some dimensions here. I'm going to call this theta, I think. I'm going to call this d theta. Okay, I'm going to call the smaller length r and the next length dr. So the big length is r plus dr. Now you go into tables and you find that the area, so the big area, so say a big, or indeed if we just look at one of these segments in general, theta and r, what's the area of it? Half r squared theta, you will find out. Theta there has to be measured in radians. So the big area is equal to half. Now the radius of the big one is r plus dr squared by the angle is d theta. Okay, and we can multiply that out. We get a half r squared plus 2r dr plus dr squared d theta. Okay, and we need to take away the small area. So the small area is a half r squared d theta. Now the difference between them, the big slice minus the little slice goes from here down and the big slice goes from there down, is this first sum minus the second. Now you get half r squared d theta minus half r squared d theta is gone. You get half by 2r dr. Now the half by the 2 gives you, or the half of 2r gives you r dr d theta. Okay, and then you also get a half dr squared d theta. Now if you think about dr and d theta as being very, very small, you've got a dr d theta and then a dr by dr d theta. So this is small. So I'm going to just call this, what will I call it? We'll call it we'll just call it epsilon. It's really, really small. Now this one is dr by epsilon. Now dr by d theta is really, really small. So this is really, really small. Now this is something really, really small multiplied by something really, really small, and basically this thing here is way bigger than the thing on the right. So this thing, and you can make it more precise than what I'm doing, is really approximately equal to r dr d theta if dr and d theta are small, which they are infinitely small, approximately 0. Okay, so this is the other thing. So you got x is r cos theta, y is r sine theta, and dA is e. So these are the three things that you have to make. Now it's something students actually have very little problem with in an exam situation, and you don't even have an exam, so you can just go into the notes and take this. Okay, now how we add up over a circular region is, say you're finding the mass, you'll find the mass of a spoke at a fixed angle, and then you'll add up the mass of all of them. So it's actually, it ends up not being too bad, although it seems a bit confusing here. So I've mentioned one way of doing it. So you find, say, the mass of, say you want to find the mass of the disc, the mass of a spoke adding up from r equal to 0 to r equal to a, and then you add up all the spokes. There is an alternative. So I'll draw the two alternatives. The spokes is the one we'll do, but I'll just write the other one here. So one of them is you fix an angle first, that'll be spokes. The rings, you fix a distance and you find the mass of a, say if it's find the mass of the disc, find this. So this would be, you'll be integrating from theta equal to 0 all the way around to theta equal to 2 pi. And you'll be finding, if you're adding up over a disk, you'll be finding the contribution to the sum from that ring. And then what you do is you add up from all the rings from r equal to 0 up to r equal to a. So you'll be integrating first from theta equal to 0 up to 2 pi, and then from r equal to 0 up to r equal to a. But I think the other way is easier. So you're adding up over a disk. You find the contribution to the sum from a single spoke. So this is a fixed angle, constant theta and d theta, and you'll be, whatever you're adding up, you're going to be adding up from r equal to 0 here up to r equal to a, where a is the radius of the disk. And after that, you'll be adding up from the spoke at theta equal to 0 the whole way around, theta equal to pi over 2, theta equal to 3 pi over 4, theta equal to 3 pi over 2, and then theta very, very close to 360. You'll be adding up all of those. And if you're adding up over a semicircle, at the top of it, you'll just go from, say, 0 to pi. Okay, so I think we're going to do, we're just going to do examples now. Okay, so a circular lamina is described by x squared plus y squared less than or equal to 16. Now remember, 16 is 4 squared, so we're dealing with a radius 4 disk. The density at any single point is given by 2x squared. Okay, sketch the region. It's pretty much done. We just need to know that the radius is 4, and then we're going to add up. So the mass one is probably an easier one to understand. Find the mass of a spoke and then add up the masses of all the spokes. Okay, so as I said, you just look at the x squared plus y squared less than or equal to a squared, and here the 16 is 4 squared, so it's a disk of radius 4. Okay, so we're going to initially fix a theta, and we're going to find the mass of a spoke. So actually what you're adding up here are the mass of little pineapple pieces from r equal to 0 up to r equal to 4. And we're going to be adding up 2x squared by dA, and remember dA here is equal to r d theta dr, and remember that x is equal to r cos theta and y is equal to r sine theta. Okay, so let's find the mass of a spoke. So the mass of a spoke, now the spoke is infinitely thin, so its mass actually should be infinitely small, and we'll have a multiple of d theta or something which does that. So we're adding up from r equal to 0. You can think of that as the pineapple piece at the middle to the pineapple piece at the end. We're integrating 2x squared. Now we're going to change the 2x squared in a second, times dA. Okay, so we're going to change everything. First of all, we're going to, so we probably don't actually need the line I just did there. So r equal to 0, r equal to 4, 2, what's x equal to? R cos theta squared. What's dA equal to? R dr d theta. Now think about you're going along the spoke. What's constant? The 2 is constant. along a spoke, the angle is the same. So at every point along the spoke, the angle that it makes with the positive x-axis is the same. It's theta. So anything with theta is a constant. Now this actually, if you multiply out, is r cos theta by r cos theta, which is r squared cos squared. So that's actually cos squared. And d theta is also a constant. So d theta, well, d theta actually is it constant? Yeah, it is. So you're imagining that actually the spoke is actually a very, very narrow pizza slice. And so it's a very, very narrow pizza slice. So yeah, the dt is a constant as well. Now, some of this can be made a lot more rigorous, but if you're interested in making it rigorous, you're doing the wrong degree. You should probably be doing a maths degree. Okay, but anyway, so we're going to take out the 2. Take out, as we said, this is actually cos squared theta. And take out d theta. And what are we integrating? From 0 to 4. Now look at all the r's. We've got r cos theta by r cos theta. So the r by r there gives us r squared. And there's an additional r, so we have r cubed dr. And as usual, the integral is fairly easy. 2 cos squared theta d theta. What is the antiderivative of r cubed? R to the 4 over 4. From 0 to 4. And now we do top limit minus bottom limit. 2 cos squared theta d theta. R equal to 4. Substitute top limit. Minus substitute bottom limit. And the 4 to the 4 divided by 4 is 4 to the 3, which is 64. By the 2, I think is this 128 cos squared theta d theta. So that's the mass of the spoke. Now it's big when cos gets close to 1, which is I think near 0, and also near. So it's over on the over here. The spokes along here and along here are biggest, and that's because the density is proportional to x squared, and the bigger that x is, the bigger x squared is. Okay, so we found the mass of a spoke, and it's multiplied by d theta, so it's infinitely small, but there's infinitely many spokes going from theta equal to 0, so the first spoke is here, the whole way around to theta equal to 2 pi. So we're adding up all the spokes from theta equal to 0 to theta equal to 2 pi. So now we find the mass of the disk by integrating from theta equal to 0 to theta equal to 2 pi, 128 cos squared theta, that should be theta, d theta. I can take out the 128 and left with integral from 0 to 2 pi cos squared theta d theta. Now, the integral of cos squared, we could have a big long discussion about it, but it's actually not that difficult, but I'm usually just going to give it to you. The integral of cos squared is pi. It's not that difficult, but it'll just be a waste of time because pretty much all of the questions I give you, or a lot of them, have it. So it's 128 pi. Does it say anything about units? No. So obviously if it was SI units, we could say 128 pi kilograms, but we can't. Okay, that's that. That's an example done. Let's look at another example. So a semicircular disk is described as x squared plus y squared less than or equal to 4. Note that this is 2 squared, so it's a disk of radius 2, but the y coordinate is positive. So we're just above the x-axis. So we'll very quickly sketch the region. Jeez, I'm cat drawn. That's worse. That's probably the best of a bad lot. Right. So there's the semicircular disk. So we're interested in the whole thing. And what we're going to find is the centroid. Now the way I've drawn it is obviously very difficult to say where the centroid is, but by symmetry, the centroid has to be along this line somewhere. So we know that x bar has to equal 0. Okay. So now what we're doing is we're adding up So, okay, sketch the region done. Maybe I should 2 minus 2, which doesn't matter too much for us. So now what we have to do is add up y over this semicircle. So what we're going to do first is we're going to find the contribution to the sum over a spoke. So that's at a fixed theta. So we're adding up y dA over this thing. So we're adding up, I'll even write it like adding up y dA. Now remember that y is or sine theta and dA is or dr d theta. I might have written it d theta dr, but of course they're the same thing. So we're adding this up and we're going from r equal to 0 here to r equal to 2. Okay, so first we're going to find the contribution to the sum from a spoke. So we get, so the contribution to the sum from a spoke, y dA, is to integrate from r equal to 0 up to r equal to 2. What did we just say? It was y, which is r sine theta, by dA, which is r dr d theta. Now along a spoke, sine theta is a constant and so is d theta, so they can be taken out of the integral. So take out sine theta d theta, and we're integrating r by r, which is r squared dr from 0 to 2. And this is an easy integral because sine theta d theta is just add 1 to the power, divide by the new power, r cubed over 3, and then do top limit minus bottom limit, the sine theta d theta. So it'll be 2 cubed over 3, that's the top limit, minus 0 cubed over 3, that's the bottom limit. So we get 8 over 3 sine theta d theta. Okay. So that's the contribution to the sum from a spoke. So now we have to add up from all the spokes. Now the spokes go from here at theta equal to 0 to here at theta equal to 180 degrees, which is equal to pi radians. So let's do this. So the integral over the half circle y dA is, we must add up theta equal to 0, theta equal to just pi, it's only a semicircle, 8/3 sine of theta d theta. So we can fix the constant 8/3 anyway, that's not an issue. And for the antiderivative of sine theta, we can go to our tables and we find that the antiderivative of sine theta is minus cos theta. And we're going to go from 0 to pi, and now we do top limit minus bottom limit. So we have 8/3 minus cos pi minus cos 0, and cos of pi is -1, so you got minus 1, which is 1, minus, which is another plus, so you get 1 plus cos of 0, which is also 1. You can bang this into the calculator, of course, as long as you're in radians, and you get 16 over 3. And then we look back at the formula. The y coordinate of the centroid is what we just calculated, the 16 over 3 divided by the area. Now we can find the area easy enough just using it's half pi r squared. R is equal to 2, so it's half pi by 4. Half of 4 is 2, so the area is 2 pi. So that's where this division by 2 pi is coming from, and you get 8 over 3 pi, which is approximately 0.8488. Now the answer mightn't look good when I put it in here. Oh no, it's going to look fine. Actually, yeah, so if here's one, it's around here. Yeah, that doesn't look too bad, because most of the area is closer to the x-axis than the y equal to 2 axis, because yeah, there's less circle up the top, if you know what I mean. So that is the position, the centroid. So that's approximately 0 along the x, and was it 0.8? Let's call it 0.85. Okay, and now we'll do another example. So a circular disc is described as x squared plus y squared less than or equal to 9. So we know that that means that the radius is equal to 3. Assuming SI units, find the second moment of area. Now here we'll just mention, if y is in SI units, y squared is in meters squared, and area is also meters squared. So you get meters squared by meters squared. The SI unit of second moment of area is meter to the power of 4. Okay, so we have, as we said, a radius 3 disc. And the first thing we're going to do is we're going to find the second moment of area of a spoke. Now I draw it here, but it can be drawn anywhere. It's like it's at some fixed theta that we don't specify. And this spoke goes from r equal to 0 up to the outside, which is r equal to 3. So we need to add up y squared dA from r equal to 0 to r equal to 3. So let's write this down. So the second moment of area of a spoke, we need to add up from r equal to 0 to r equal to 3, y squared. Now the y is r sine theta, by dA, which is r dr d theta. Okay, so now along the spoke, as I said, it's just some fixed angle. So the d theta is fixed, and this is eventually, if I multiply out sine squared, that's also a constant. So I can fix sine squared theta d theta, and what am I left with? Well, I've got r by r squared by another r, which is r cubed. So I'm integrating from 0 to 3 r cubed dr. I feel like I might have missed an example. Oh, I got through them. Okay, sorry. Now I've probably gone very fast in this. Pause me, rewind me, slow me down, whatever it needs to be. Okay, so this is equal to sine squared theta d theta, and now we just have to integrate the r cubed. So as usual, add 1 to the power, divide by the new power, and now we do top limit minus bottom limit. So this is sine squared theta d theta. Substitute in top limit, 3 to the power of 4 over 4 minus 0 to the power of 4 over 4. And the 3 to the 4 is 3 by 3, which is 9 by 3 by 3. 9 by 9 is 81 over 4. So I get 81 over 4 sine squared theta d theta. So that is the second moment of area of a spoke. And if you look at it, which one will be biggest? So like the spokes like this don't have much of a second moment of area about the x-axis. The one like this will be biggest. And so when theta is closer to pi over 2 or minus pi over 2, this is going to be bigger. And indeed that's the case, because sine is big when when the input is close to pi over 2, and sine squared is big when the input is also close to minus pi over 2. So that's the second moment of area of a spoke. So if we want to find the second moment of area of the entire disk, we can add up from theta equal to 0 spoke to theta equal to 2 pi spoke. Now you might feel there, because you have 0 to 2 pi, you're actually, so the spoke that goes in the positive, along the positive x-axis, is counted twice perhaps. But remember that each of them, like, it's multiplied by d theta, so it's infinitely small. So it doesn't actually matter if you count them twice. You actually do that all the time. Like, say if you want to find the area of this shape, you find the area of the rectangle, you find the area of the triangle, and you add them together. You never worry about the fact that you added the area of this strip twice, but it has a 0 area, so adding it twice doesn't really matter. Okay, so what have we got? 81 over 4 sine squared theta d theta. We can fix the constant 81 over 4, and then we're integrating from 0 to 2 pi sine squared theta d theta, and I hope in the question I gave the hint, the integral over 0 to 2 pi of sine squared is just pi. So this is 81 over 4 times pi. I would just keep it as that and put meters to the power of 4, but you're an engineer, you might want to get a decimal approximation. So you do 81 over 4 by pi, and you would get 63.62 maybe. Meters to the power of 4. So that's all your double integration over a two-dimensional shape.